Thanks for coming, everyone. I'm going to give a project update for AMReX. AMReX was not one of the founding projects of HPSF, but it joined kind of shortly afterwards. So yeah, I'm Andrew Myers. I'm one of the developers. I'm also the TAC representative for the AMReX project. And so I checked this morning, and our contributor count on GitHub was 194. So obviously a lot of other people have contributed to the stuff I'm going to be talking about. I want to specifically highlight Wei-Chin Zhang, Axel Hubel, Alex Sin, and Ann Almgren as people whose work I'm going to be highlighting here. If you're not familiar with our project, so we're an adaptive mesh framework. We're a block-structured adaptive mesh framework, so not the tree kind of AMR. So in block-structured AMR, the solution is defined on a hierarchy of levels of refinement, kind of like I'm showing here. This is one of our tutorial codes that solves the advection equation giving a prescribed velocity field. So AMReX, you have support for mesh data and particles that are defined on a hierarchy like that. It does things like ghost cell filling and communication in between levels of refinement that you need to do when you do mesh refinement. We also have a number of different linear solver options for if you want to solve something like a Poisson equation on a hierarchy like that, support for embedded boundaries. And we run on all the major different GPU vendors, NVIDIA, AMD, Intel, and also have OpenMP support for CPUs. This is an application sort of highlight slide that I like to show just to give a sense of the breadth of applications that are using us. There's codes that do astrophysics and cosmology, combustion, particle accelerator modeling. You'll be hearing from one of those, WarpX, right after this talk. A lot of these are doing some flavor of CFD, but there's also a lot of PIC codes represented, and there's also models that are doing something more exotic for us, like agent-based models for epidemiology and models of fungal growth and things like that. In a lot of cases, these codes were built in collaboration with us, but in some cases, people just downloaded AMReX off GitHub and used it to build something pretty non-trivial. So I think that's gratifying to me as a developer. So I want to spend most of my time talking about just new developments over the past year, or since the last time we had HPSF. So this isn't a code development or a new feature per se, but it's something that's very nice for us and something that was enabled by our participation in HPSF. So we now have CI running on AMD and Intel, and also NVIDIA GPUs. These are running on the Frank cluster at Oregon, kind of an outgrowth of the CI working group. We have a GitLab mirror that's hosted on SPAC's GitLab page. So the way our CI worked before this is we had just a test machine that we kept at LBNL. It was running on an old NVIDIA gaming card, and we would just run our tests and a bunch of our applications tests overnight, every night. Now with this, we're running on kind of real HPC cards, and we're also able to, so it still runs every night. The GitLab mirror does kind of a regular pull, but we also have this capability to opt in to GPU testing on a specific pull request. We decided not to do it on every single push to the repository, but we can choose to run it for select PRs. And one of the authorized maintainers leaves a comment. This triggers a workflow that uses GitLab's REST API to start a pipeline. And there's an example there. So this is an example of our test running on 3 different architectures. Then a post stage runs that goes and puts the comment back on the GitHub telling you whether it passed or not. So yeah, this is very nice, and it's I want to especially thank this HPSF CI working group and Zach Gilbreth specifically for helping us set this up. And this is just showing that the test, in fact, ran. Okay. Now I want to talk a little bit about some more code developments and features. So one thing that's new is a true multi-dimensional array view called ArrayND. AMReX always supported a 4D array view, so we would say there's like space dim coordinates plus 1 component. And you used it kind of like this. So you define a box that's like your index space, and then you define a fab, which is actually this actually owns the memory, and then you can make this array view object and then do stuff with it. So we now have support for in dimensions like a standard MD span or a Cocos view. So here's us defining a 5-dimensional box and a data pointer, and then using that to create the view. And a thing about this is it supports negative indices and offsets, which we find are very nice for when you're doing stencil calculations and you need to do access ghost cells and things like that. And we had some support for things like this, but this basically has unified it into one syntax for doing it. Another thing that's nice, and this is mainly the work of Alex Sin, who's one of our contributors from Germany, is a stream-ordered memory allocator. So this is to solve the following problem. So this is a loop over a multifab, which is sort of mesh data defined on a collection of boxes. And often you need temporary scratch space on a per box basis. And if you're not careful, this can be dangerous on the GPU because the GPU kernel might not be finished running at the time that this object goes out of scope. And we've had a number of different solutions to this over the years. But the current one, and the one we like the best, is this stream-ordered memory allocator. Essentially, there's a free async function that doesn't actually free the memory until the next time a stream synchronize is called. And if too much memory gets used, it will synchronize for you. So yeah, in the past, we were using CUDA and HIP's native stream-ordered allocation, and then a different, less efficient strategy for SYCL, but the new implementation works on all that, and is also more memory efficient because it uses AMRex's pre-allocated arena. Another cool thing that was added recently, and this was the work of Axel Hubel, but support for SIMD operations. So previously, if you wanted to do SIMD in an AMReX code, there wasn't really support for it. You needed to do pragmas or try to rely on auto vectorization. So now what it looks like is something like this. And this requires the VIR SIMD library. So you essentially have a special vectorized version of the functor that you've created using a mixin class, and then you're calling a special SIMD version of parallel4 that knows how to unroll the loop based on the SIMD width, and then you're calling, load and store operations that, if you're compiling with SIMD support, load vector registers, and if you're not compiling with SIMD support, we'll just access that array element. So Axel found some very nice speedups using this on the ImpactX code, and especially for kernels that are heavily compute bound, which ImpactX has a lot of. Another new capability is with regards to our FFT capabilities. So we provide a parallel FFT that basically, under the hood, to do the individual FFTs, it's either using FFTW, QFFT, RockFFT, or 1MKL, but it kind of provides a wrapper around all that. But then also when you need to do communication, we're using the AMReX parallel copy functionality to do that. So you don't have to be limited in the way you're doing your domain decomposition because you're doing FFTs. And we found that doing it that way is quite efficient. And there's also FFT-based Poisson solvers that support a number of different boundary condition types. So things that are new, complex to complex transforms, and also batching. So you can run a bunch of FFTs of the same size at the same time on the GPUs. Another thing that's new, so there's improvements to the AMReX parser. So there's a math parser that can evaluate expressions like that one on the device. And this is nice because people like to write text-based input files that have a density profile or something in it, so they can do that and still run on the GPU. So things that are new are support for expression chains, like that one. If A is less than X is less than B, do this. And you can also mix mathematical expressions with user-defined functions now. We've made a number of improvements to our particle classes. So some of the design decisions that were originally made, you had to specify a lot of stuff at compile time, which made a certain amount of sense before the Python interfaces existed. It actually simplifies maintaining those a lot if there can just be like one. You don't have to have a bunch of templates. So we've switched to a mode of being able to define a bunch of stuff or switch a bunch of stuff out at runtime. So this is explaining how, this is just showing an example of how you can define one kind of particle container and then set it to use pinned memory at runtime, which wasn't possible in the past. I guess a very practical thing that we found useful with the AI coding agents is just telling them to find bugs in the code base. So we did this with both Codex and Claude, and they found dozens of issues. They're not always right about there being a bug, and they're not always, the patches they suggest aren't always correct. But in some cases, we found things that were, genuine bugs, and I've been there for years. It's often pointing to a gap in our test coverage, so kind of rarely trodden code paths. Like an example of one was you had to be doing a checkpoint restart with particles using the HDF5 backend. You had to have a different number of levels in the file that you were in the simulation you were trying to run. And you had to be trying to read on fewer MPI ranks than you were using in the simulation. And we didn't have a test for that, but in response to these bugs, we wrote one. Even in cases when they're not real bugs, it often points to something that we could be clearer about, like we're making an assumption that we know we can make because we have the full context, but the agent doesn't really know that. So often it's pointing to we should add a comment there, or we should put an assertion or something like that. So in terms of what's next for AMReX, well, there was a lot of discussion at the panel this morning about reduced and mixed precision. As they said, the design of GPUs is not really being driven by traditional HPC applications. And as a result of this, the FP64 performance isn't really getting any better in the latest architectures. So what we need to do is basically we have to actually start thinking about when we really need double precision instead of just defaulting to using it because we can. So some examples of ways that AMReX needs to be extended for this. We need to allow for more flexibility in the way people represent particle positions. There's schemes where you store a particle's position as a cell ID using an integer, and then you store its offset within its cell that's more accurate than just using a single floating point number. And there's also stuff you could do thinking about doing mesh refinement with different precisions at each level of refinement. It kind of naturally fits into the idea of mesh refinement. So that said, I'm almost out of time. I wanted to say that we're having an AMReX project meeting on Thursday in the Rock River room. We'll be hearing 15 talks, a bunch of different applications ranging from astrophysics to fusion energy, a couple talks about using AI agents for either code development or like more workflow stuff. And we'll also have just lots of discussion of where we want to go from here. So thanks. So there's a couple papers to cite and a couple QR codes to scan for our documentation and a training tutorial. Thank you. Happy to take questions. Yes. Oh, should.
So I'm curious about the AI-assisted bug finding that you did. Were you guys already running a bunch of static analysis and there's good tools before?
We had some like linting. Oh, sorry. We did have some automatic like code linting things that we use, and also memory check. I'm forgetting the name of the tool, but like a Clang sanitizer. Yeah. So there are tests like that are being run, but we had to have a test that specifically ran that branch of the code, which I think we didn't have in some cases.
Were you running the client ID check with some security related one? Are you running that?
I don't think we're running the security-related one right now. What's it called?
I don't have it on top of my head.
Okay.
But I can show you.
Okay, yeah, let's talk about that.
Thank you. We're next.
Oh, hi. So I have two questions. I'm not going to double dip. I'm just going to ask my first, and maybe if there's time. Okay. So, so you had mentioned at the top that you used to collaborate a lot, to on a lot of those applications that you showed us, and increasingly people have been doing on their own. But I think as part of the sustainability financial models we talked about at the beginning of the conference, I still think there's a role for doing that type of collaborative work. Like, I think it's very important to involve code libraries and applications to push the boundaries of what our science can do. And so I was trying to better understand like, where do you see that line between, like, in terms of deliverables, like, do you think that like a 1-year grant, for example, with 3 or 6 months of developer time and like feature complexity. So like, what are some examples of where you think making a change to the code has advanced science and could support writing more complex applications? Or I mean, do you work off of like a roadmap, or how do you brainstorm some of those things?
It is often kind of project driven in that there'll be a collaboration with, I don't know, say the WarpX people. And so there's a specific grant to study a specific science problem, and it's about what's needed in order to do that. At the other end of the extreme, I guess answering questions on GitHub, fixing bugs and things like that are, we just do that for free. So there's kind of a range of different, I guess, modes there. But yeah, I mean, sometimes we have to say that, like, okay, this new feature, we're happy to talk you through how to do it, but we don't have the developer cycles without, some kind of funding.
All right, I think we have to stop soon. One very quick question from Steven.
Yeah, I was just wondering about that SIMD thing. Is that, I didn't quite catch, you're speeding up GPU code with that, or that's for CPU applications?
For CPU applications
Okay,
only.
all right. And that would be better than using, say, NSIMD in the loop?
So Axel, since you implemented this, do you want to take that question?
It would be better than what?
NSIMD. So currently we have a AMReX code that uses NSIMD for CPUs.
I don't know that code. We have to talk about this in a break.
Thank you.